All right, let's get going on our practice exam. So first up, we want to convert liters to milliliters. I can do that with a conversion factor, 1,000 milliliters per 1 liter. So I need to multiply by 1,000. The liters will cancel, and I will have 5 milliliters. Similar for the second one, except because this is centimeters squared, I need to consider that. So let's think about how to get from centimeters to kilometers first. There's 100 centimeters in 1 meter and 1,000 meters in 1 kilometer. But because it's squared, I need to square each of the conversion factors as well. So when I put this in my calculator, I'm not going to divide by 100, I'm going to divide by 100 squared. And I'm going to put that in parentheses just to make sure I do it right. And then divide that by 1,000 squared. And that's my answer. I'm going to put it in scientific notation because it's a tiny number, 2.85 times 10 to the minus 9th. And then the centimeters squared cancels, the meters squared cancel, and this would be kilometers squared. Remember, non-zero digits are significant. The 0 in the middle is significant. The 0 at the end of a decimal is significant, but the 10 to the 9th, or the, whatever it says, 10 part is not. So just 4. Next up, aluminum. I can look on the periodic table and see that it has 13 protons. So any answer that doesn't say 13 protons, I can just get rid of those. Right? Not that, not that, not that. If this was an atom, an aluminum atom, it would be 13 protons and 13 electrons. That means they're equal. But this is an ion, and it's a 3 plus ion, meaning it's missing 3 electrons, so it would be the 10 electrons. Next up, an ion is something with the charge, so that would be that first one, boron. NaCl would be an ionic compound. Helium would be an atom, and the carbon-14 would be an isotope. All right, we've got 3 lead, sure. The 2 gets multiplied through, so we've got 2 phosphorus, so C, D, and E are out, or C and D are out. And then the 2 times 4 means we have 8 oxygen. All right, to convert pressure, we will pull out our equation sheet here. This is asking us to go from millimeters of mercury to kilopascals. I see here there's a conversion between millimeters of mercury. 760 millimeters of mercury is equal to 101,325 pascals. And then I know kilo means there's 1,000 base units in 1 kilo unit. So I will set that up so that my units cancel. And then I have 654 times 101.325 divided by 760 and then divided by the 1,000. I want my answer to be to 3 sig figs, so I'll round it to 87.2 kilopascals, which is A. All right, next up, separating into ionic species, major ionic species, we're going to separate up into sodium and carbonate. Remember, 2 types only, so that's 2 sodiums and 1 carbonate. The sodiums will not stay stuck together, so like A and B, and the carbonate will not separate like C and D. It will be E, sodium plus and carbonate 2 minus. There are 2 sodiums, but that doesn't matter. There could be 100 if I put in multiple molecules. For redox, I'm looking for a charge to change, and I see it right away in A, where aluminum was by itself, so it must be 0, and then it became 3 plus. But I'm just going to go through and kind of check the rest. Everything's part of an ionic compound and stays part of an ionic compound, so nothing else looks like it's changing charge. It's +1 on the left, it's +1 on the right. It's +2 on the left, it's -2, or whatever, +2 minus whatever. It stays the same, +2, +2. So as long as nothing's changing charge, but when it has when it's an ionic compound on one side and it's all by itself on the other, that's when it's usually changing charge from 0 to something else. So that looks like just A in this case. All right, here we go with solubility rules. We need to first predict what our products would be. So this would be copper switching places with the barium and copper bonding to the chlorine. Let's write in all the charges, +2 minus 2, +2 minus 1. So copper and chlorine would be CuCl2 to make it neutral. And then barium 2 plus, sulfate 2 minus would be BaSO4. The rules say chlorine's usually soluble, so that would be aqueous. Barium sulfate would be my solid. I don't need to balance it. I don't know what I was doing there. All right, so I see barium sulfate is my solid, and the only one that has that as a choice is C. All right, oxidation numbers for each atom. So I'm going to just write in all the atoms I have. So I have manganese, I have oxygen, I have aluminum, oxygen. And then I can write in what I know, which oxygen is always -2. So I'm going to write those in. And then I'll figure out what the charges are. So -2 times 4 is -8. The whole thing has to add up to -1 because of the charge, which means the manganese must be +7. Here we have -6, 3 times -2, which means the aluminum must be +6. Since there are 2 of them, it gets split in half and they're +3 each. Here I have 7, so -14, and it has to add up to -2, which means it's +12. Again, there's 2, so I split that up and I get +6 each. All right, for balancing, I see 8 carbons, so I'll put 8 over here. 18 hydrogen, so I'll put a 9 by water, and now I've got just oxygen left. I've got 9 plus 16 is 25 oxygen on the right. Here I've got 3 in that molecule, and so the 22 more that need to be accounted for, which means I need 11 of the O2 molecules. All right, magnesium is a +2, that's from the periodic table, and phosphate is a polyatomic ion that always has a charge of -3. PO4, 3-, so when I put those together to make them add up to 0, I'll need 3 magnesiums for +6 and 2 phosphates for -6. All right, magnesium again, +2. Nitrogen is -3 from the periodic table or from the charges I can figure out. And then magnesium, and then nitrogen gets changed to nitride because it's from the periodic table, IDE ending. Ca2+ and F- would be CaF2 to make it neutral. It has to add up to 0, and then calcium fluoride. Only when there's no metal, like in N2O4, do I include prefixes, right? So this is 2 nonmetals, then I can do the prefixes. Finally, I can see nitrate is -1. That's a polyatomic ion I memorized, and there's 2 of them, so the iron must be +2. And then I include that in my name because iron is in the transition metals. So iron 2 nitrate. Protons, neutrons, electrons, and mass number. I look at bromine. It told me it's 35 as the atomic number, but also I can get that from the periodic table. So it's 35 protons. The neutrons are the mass number minus the protons. 81 minus 35 would be 46. Neutrons. There's no charge written, so it must be neutral, means there must be the same number of electrons as protons, so 35. And then finally the mass number is that 81, the protons plus the neutrons. For half reactions, remember I want them to be able to be balanced, which means 1 element per half reaction. So silver in one, copper in the other, and then keep everything on the correct side of the arrow. So if it was on the left, it stays on the left. Then I need electrons, and I want the overall charge to be equal. So the first one has a 2+ on the left and a 0 on the right. So I need 2 electrons to make it 0 on the left. And on the bottom one, it's 0 and 2+. So I put 2 electrons on the right to make it 0. The oxidation is the one where the charge went up. So it went from 0 to 2+. The reduction's where it went from 1+ to 0. All right, now I need, to figure out the molar mass, I need the formula. So lithium is a +1. I know that from the periodic table. Carbonate is a polyatomic ion, so I know that's a -2, which means it must be Li2CO3. And now I can figure out the molar mass. Lithium is 6.941, so 2 of those. Carbon is 12, and 3 oxygens, which are 16. So I get 73.882. That's grams per mole. That's the molar mass. All right, I can use that molar mass to convert grams to moles. 6 grams, I'm going to divide by molar mass so that I get the grams on the bottom and moles on top. So 6 divided by the molar mass. I just want 2 sig figs because 6.0 grams has 2 sig figs, so the zeros don't count, so 0.0 and then 81, and that's how many moles. To go from moles of compound to moles of carbon, I just have to look at the formula, and I see in 1 lithium carbonate, there's only 1 carbon. So in 1 mole of lithium carbonate, there's 1 mole of carbon. So in 0.081 moles of lithium carbonate, there's 0.081 moles of carbon. And now I can convert that to grams using the molar mass of just carbon, which is 12. I'm multiplying so that the moles will cancel this time. There you go, 12. Just came from there. So I'm just going to multiply 0.081 times 12. Again, 2 sig figs for the answer. Okay, this doesn't say limiting reagent, but this is a limiting reagent problem. They gave me how much of each reactant, and they're asking me for how much product. So I'm just going to treat each one separately. I'm not going to combine these masses. I'm just going to start from, if I use up all my calcium, how much calcium oxide could I make? So first I'll use the molar mass to figure out how many moles of calcium I have. Then I'll use my stoichiometric coefficients to figure out how many moles of calcium make how many moles of calcium oxide, and I see 2 and 2. And now I need the molar mass of calcium oxide to get to grams of calcium oxide. So that's the 40.08 plus 16. And if I put this all in my calculator, this is going to tell me if I use up all my calcium, how much calcium oxide can I make? If I can put it in my calculator correctly. Oh, yeah. So if I use it all up, I want 3 sig figs, I can make 5.88 grams of calcium oxide. Now I do the whole thing again, starting from if I use up all my oxygen, so starting from 2.80 grams of oxygen. Molar mass of oxygen. Now the molar mass of O is 16, but this is the O2 molecule, so I'm going to multiply it by 2, 32. And then I need the stoichiometric coefficients. So now 1 mole of O2 makes 2 moles of calcium oxide. And then the molar mass of calcium oxide I already have calculated from before. So if I put this one in, now this is if I use up all of the oxygen, how much calcium oxide will I make? And I can make 9.81. Once I have both of these numbers, I just cross out the bigger one. I'll never make that much. I'll run out of calcium. I'll only ever make 5.88 grams. So that's how much I can make. That's the theoretical yield. And if it asked me for the limiting reagent, it would be calcium, the reactant that got me there. All right, atoms to grams, I need to get to moles first. So I'll use Avogadro's number to convert atoms to moles. 6.022 times 10 to the 23rd atoms per 1 mole. So I'll put that on the bottom. And then I need the molar mass. This is just nitrogen atoms. So I need the molar mass of just nitrogen, N, which is 14. And then actually the second question asks me for moles. So this is exactly the same problem except without that 14 part, right? So I can just do the Avogadro's number part. That would get me to moles. All right, let's put it in my calculator. For the first one, all right, it's pretty small, so I'm going to convert it. You could leave it longhand, but I'm going to convert it to scientific notation. I want 3 sig figs because my starting data had 3 sig figs, so 1.20 times 10 to the minus 4th. And then I'm just doing the same thing, but I'm just going to delete that times 14. And I get 8.60 times 10 to the minus 6th. All right, for percent composition, I'm going to first need the molar mass of the whole compound, the tin oxide. So I just need to pull out my periodic table. I see tin is 118.7. and then 2 oxygens, so 16 and 16, so 150.7 is the molar mass of the whole compound. And then for percent composition, remember it's how many are in the formula. So for tin, it's just 1 times the molar mass of the thing, which in this case tin is 118.7. And then the molar mass of the whole thing, 150.7 times 100 to make it a percent. For oxygen, there's 2 oxygen per molecule. 16 is the molar mass of oxygen. 150.7 is the molar mass of the whole thing times 100. All right, put those in. Sorry for the glare. All right, I get 78.77. And then two times 16 divided by 150.7 times 100, 21.23. I should check my work and make sure they add up to 100, so I'll do that. And thumbs up, they do. All right, molarity, remember, is moles of solute. In this case, that's ethanol on top, liters of whole solution on the bottom. So I have grams of ethanol. I'm going to have to convert that to moles. I'll use the molar mass to do that. So 24 for the carbon, 5 hydrogen, 1 oxygen, and 16 plus 1 more, so a total of 46 grams. And I need to divide to get the grams to cancel. 0.630, and that would be my moles of ethanol. Then I just take my 545 milliliters, convert that to liters. I did that just by moving the decimal 3 places to the left. And I got 1.16. Remember, the units for this could be moles per liter, or you can write it as 1.16 big M. Either one is fine. All right, and then finally we're going to mix AgNO3 and MgCl2. So again, let's think about all the charges ahead of time. So +1, -1, +2, and -1. So silver and chlorine would just be +1, -1, 1 of each. And the magnesium and nitrate would be MgNO3, 2. Nitrate is always soluble, no exceptions, so that would be aqueous. Oh, let me balance it. Hold on, there's 2 nitrates, so I put that. Now there's 2 silver, 2 chlorine. All right, we're good. So aqueous here. Chlorine is usually soluble, but silver is an exception, so it would be a solid, and so that would be my precipitate. So that's my full molecular equation. For ionic, which is my next step, I need to separate anything aqueous. So 2 silvers, 2 nitrates, 1 magnesium, 2 chlorines. Remember, everything's separating from itself. All those subscripts get moved out in front, so 2 Cl minus. The solid stays like it was, so 2 AgCl solid, and then the magnesium and nitrate get separated. It's magnesium 2 plus and 2 nitrates. Now I look for things that cancel. The silver went from aqueous to solid, so no. Nitrate looks exactly the same, so that gets canceled. Magnesium looks exactly the same, so that gets canceled. Chlorine went from aqueous to solid, so no. So then I just recopy what's left. 2 silver pluses, 2 chlorine minuses, making 2 silver chloride solids. You can leave it like this if you want to, or you could cancel out those 2s since they all have a 2 in front, and you could write it as just 1 silver plus 1 chlorine minus, making 1 AgCl. Either one is fine. All right, so this says I should use the ideal gas law. It gives me some information. So let's write down the ideal gas law first. PV equals nRT, and I'm looking for the pressure, so I'll solve for that by dividing by volume on both sides, and I get nRT over V. And so for N, I need the moles. I have that, 3.50 moles. Remember, R is always the gas constant, 0.0821 liters atmospheres on top, moles in Kelvin on the bottom. It's on your equation sheet. And then for temperature, it is 47 degrees, but it has to be in Kelvin, so 320 Kelvin. And then in the denominator, I will just have the volume, 5.20 liters. The moles will cancel, the liters will cancel, the Kelvin will cancel, and I will get a pressure in atmospheres as it asks for. All right, 3.5, 0.0821, 320, and divide by 5.2. Whoop, there we go. And I got 17.7 to 3 sig figs. I guess it should probably be to 2 because of the temperature, but once I added it on, I ended up with 3 sig figs on my temperature, so I put 3. All right, and then finally, if a child releases, okay, so this is a volume, I've got a temperature, I've got a pressure, and then I've got another temperature and another pressure, and I want a different volume. So let's think about what's constant. That would be R, the gas constant, and N, the number of moles. That didn't change, it's all trapped in a balloon. So I'm going to solve for whatever is equal to the constant, so PV over T equals a constant, and then I can put in my subscripts. P1, V1 over T1 equals P2, V2 over T2. Now I'm labeling everything. So the stuff at the beginning, volume, pressure, and temperature, I'll label all with ones. I do want to convert that temperature to Kelvin. So I'll do that now. And then the other stuff, the second half after it's risen to a new altitude, that's all the twos. So again, I need to convert this temperature to Kelvin. And that's my P2, and then it's asking for the volume, so V2 is my unknown. So let me solve this equation for V2 by getting it by itself, so I'll multiply by T2 over P2 on both sides to get V2 by itself. And now I just have to carefully plug in everything. The twos and the ones are all kind of scrambled, so I'm just looking at what I've labeled, and because I've clearly labeled it, it won't be too confusing to put the right things in the right places. And then P2 and T1. So my Kelvin and my millimeters of mercury cancel, and I'll get an answer in liters. 38.65. Again, I'm just being careful that everything ended up in the right place and putting it all in my calculator correctly. When I have two things in the denominator, I like to hit enter after the first one and then divide again so that my calculator can't get confused, and then I get 10.2. And the unit would be liters. That's it. Good luck.